Hello class. This lesson we're going to learn about similarities. So first I'd like you to think about what the word similar means to you. That could be a definition outside of math or a mathematical one. And then I'll show you what our formal one is. So in this class, similar figures, they look the same. It's like the same shape, but they could be different sizes, or they could be transformed according to the basic rigid motions. So specifically, similarity transformation is what we get if we take basic rigid motions, but we add in the possibility of a dilation. And so when you do that, you can calculate scale factor by multiplying all of the scale factors in the dilations. Let's see, when there's no dilations, then everything's the same size, so the scale factor will be 1. And so we say that figures are similar if we can map one onto the other with a similarity transformation. So in this example, these two smiley faces are similar, right? It's the same shape. One is just smaller than the other. So we could do similarity transformations, go from one to the other. They're well scaled. This one though, these two faces aren't well scaled, so there's no similarity transformation that will take you from one to the other, because the dilation is going to preserve that characteristic. So in this example, we want to just state the transformations that we'd have to perform to go from figure 1 to figure 2. So try writing those out, and we'll talk about it together. So first, we would have to dilate figure 1 so that it was as large as figure 2. So we'd have to enlarge it with a scale factor bigger than 1. And then after we enlarged it, we would have to reflect it over a line. So that line would be the perpendicular bisector of any of the corresponding segment connecting corresponding points in these two figures. So you should have said a dilation followed by a reflection. You could have given a few more details. Same idea here. How do you go from S, looks like that snow cone, over to S prime? What would you do? So first, you would do a dilation, another enlargement. You would dilate S until it was the same size as S prime, and then we would rotate that image around that center so that it lines up with S prime. Now, what about in this case? It looks like these two pictures could be similar, but it turns out that when we check with measurements, they are not. So let's see why that's true. So if we measure, let's see, WX and AB, let's measure the long segments, I should say. So AB measures 3 centimeters, WX measures 2 centimeters. So if we think of this as a reduction, scale factor is 2/3. So if there is a similarity transformation, so if they are similar, then we should get the same scale factor over here. So CD is 2.3 centimeters, and YZ is just about 1.3 centimeters. But when we divide those, we do not get the same ratio. So these two figures are not similar. So let's write that out. We would have to have the same scale factors of 2/3, but the scale factor for the shorter segments gives us 13/23, right? If you multiply the top and bottom by 10, we get 13/23. So there's no possible similarity transformation that will map the larger figure onto the smaller one. So here are some important properties of similarity transformations. This first one basically says whenever you have points that aren't the same, whenever you do a similarity transformation, the images of those points will not be the same. This is a mathematical property called one-to-one or injective. So you'll see this more in algebra 2, but if you want a little bit of fancy knowledge from vocabulary, that's what this property is called, one-to-one. And also, any point that you get from a similarity transformation had to come from some point in the pre-image. This is a math property. I know it seems silly, but it is important. This is a property called onto. So, or surjective, another fancy term. You don't have to memorize what's in blue here, just for knowledge, just so you know more. And there's always a scale factor so that a pair of points with these images satisfies the property here. So you can always multiply the original length by the scale factor, and that will give you the length of the segments, the image segment. A little bit more information here. Just remember, you can always multiply those scale factors to figure out what the scale factor is of the entire similarity transformation. So, like we had before, you see lines get sent to lines, rays to rays, segments to segments. Parallel lines stay parallel. Angles stay congruent. And circles are similar to each other. And we're going to look at that in a little bit. So this is an important property. We say that we want to know, is any figure congruent to itself? So this symbol we use for similarity is the tilde. That means A is similar to B. So do we believe that A is similar to A? Is A similar to itself? Yeah, it seems reasonable. Anything is congruent to itself, so we know that if it's congruent to itself, it's got to be similar to itself. So how can we map A onto itself with similarity transformations? So this is called the reflexive property, and we've seen that before. So a lot of ways you could think about it. We could say we could rotate 0 degrees or 360 degrees. We could dilate with a scale factor of 1. There's lots of possibilities. So food for thought here. Do we think that, change this, if A is similar to B, that B is similar to A? So if we can map A onto B, can we map B onto A? Yeah, we just have to kind of reverse the steps we did. This is called the symmetric property. And so let's look at some examples. So if we translated using vector xy, we would just translate using vector yx to undo that. If we dilated with the scale factor of 2, we just dilate with the scale factor of 1/2. So we can undo that and go backwards. So this satisfies this symmetry property, or symmetric property. And finally, if A is similar to B and B is similar to C, is A similar to C? Yeah, that's a transitive property. And how do you know that? Well, if you can do a transformation, a similarity transformation from A to B, and a similarity transformation from B to C, if you just put those two similarity transformations together, you will go from A to C. So similarity satisfies these three properties: reflexive, symmetric, transitive. And those properties together with a set that you talk about is something called an equivalence relation. So another fancy term. You don't have to memorize that, but it's good to know. So how do we show that circles are similar to each other? So a few different cases. What if there are different centers, but the radii are the same length? How can we map one circle onto the other? Think about that. There's multiple possibilities, but one straightforward way is to do a translation along a vector that will take one center onto the other. And that shows that the circles are similar, because a translation is a similarity transformation. What if they have the same center, so they're concentric, but what if the radii are different lengths? How can we map one onto the other? Well, we have to do a dilation. Dilation with that center of the circle. And the dilation, we could use scale factor. For the dilation, we could use scale factor of r prime over r. So if we enlarge the smaller circle with that scale factor, right, r times r prime over r, the r's are going to cancel, you're just left with r prime. And the third case, what if they're different sizes, but they have different centers? Well, you just combine what we did in the first part to get first and second parts. So you would just translate them so the centers line up and then dilate one. So any circles are similar to each other. And finally, some important properties. So we've already talked about this first part before. We know that they're similar if there's similar transformation from one to the other. So we can say triangles are similar by just writing out the names and putting the tilde in the middle, similar to what we did for congruent, but now it's a different symbol. And we also know by this theorem on similar triangles that corresponding angles are equal in measure, and that corresponding side lengths are proportional. So if we divide corresponding side lengths, we will always get the same number. In this lesson, we learned about similarity. So here's a little overview of what we learned. Thank you for watching this video.